3.8, we're going to discuss Newton's method. Newton's method is for when you need to try and find where a graph crosses the x-axis. It's zeros, it's x-intercept. So there's a lot of different ways you can refer to this point, but we want to try and find this in an iterative approach. That is, by doing something again and again and again until we refine our guess and get something pretty close. So Newton's method is going to start out by assuming that you've got an initial guess as to where this point is. We don't know where it is. We're going to try and find it. But we've got some initial guess. We'll call it x sub 0. So at x sub 0, that puts you on a point on this function, and hopefully it's reasonably close to the point you're seeking. But we want to do better. So how could you do better? Well, let's find the equation of the tangent line that runs through this point. What two things do I need to know to find the equation of a line? I've got the point. What else do I need? Slope. And the slope of the tangent line is determined by the derivative. So slope here, m tan, m tan equals f prime at x sub 0. Let's put that together with this function, y minus y1 equals m times x minus x1, and come up with the equation of the tangent line here in very general terms. So that'd be y minus f of x0 equals f prime of x0 times x minus x sub 0. All right, so that's the equation of my tangent line. But if I'm going to try and find this point, I know something about the points on this line. In particular, that point right there. What can you tell me about this point? There's something we know here. Not the x, it's y is 0. It's the x-intercept, so it's y coordinate is 0. So if I put in a 0 here, so 0 minus f of x sub 0 equals f prime of x sub 0 times x minus x sub 0. What I want to do is I want to figure out where's x. Where's that next point, which hopefully is closer to the actual real root of this problem. So let's just divide both sides by f prime. That would give me minus f of x sub 0 divided by f prime of x sub 0 equals x minus x sub 0. Keep in mind, x sub 0 was our first guess. If I move this to the other side, then I get x sub 0 minus f of x sub 0 over f prime of x sub 0. And let's call that x sub new. So you've got an old guess minus a little bit of a correction factor gives you a new guess. And what we're hoping is that that new guess is even closer to the actual root. Once you get the new guess, put it back in here and do the process again. And keep on doing it until your guesses get closer and closer together until finally there's no change at all in those guesses. And that's Newton's method. It's what's called an iterative method for finding the roots of a polynomial. Now everyone's got a handout here, right? Newton's method. Let's take a look at that handout and work our way through it. So here's some function, y equals x to the fifth plus x minus 1. And you really can't find the solution to this with some fifth degree version of the quadratic formula. It just doesn't exist. We don't have a formula that goes for this. That poster in the upper right hand corner talks about that kind of a problem. But suppose you wanted to find where this graph crosses the x-axis. You want to find its roots. We can still do that. We're going to need a few things though. So one of the things we're going to need is the function. The other one we're going to need its derivative. Take out your calculators and let's put those into our calculators. So into y1 let's put x to the fifth, x raised to the 5 plus x minus 1. And then the derivative of that, you should be able to get the derivative pretty easy. That's just a nice polynomial function. The derivative is going to go into y2. Make sure they're in y1 and y2 respectively. Otherwise, you'd have to tweak this a little bit. If you were to graph it, you'd get something that looks like this. Let's take a very rough and ready initial guess. Let's say that x equal 0.5. That's our initial guess as to where this graph crosses the x-axis. Obviously, you could do better, but I just want to keep it simple here for the start. So after we get this entered, hit the second key, then the mode key to exit back to the home screen. And let's take 0.5 and store it right there, store key next to 1, in x. So it should look like this. Your calculator should respond like this. So type in the 0.5, right? So 0.5, and then the store key is right here. So press the store key, and you want to store it in x, and x is right here next to the alpha key. So your calculator should respond like this. Now, that's your initial guess. What we want to do is we want to set up this on kind of an iterative basis. You type in the old guess, you modify it by a little bit, and then you get the new guess. So the commands to run through Newton's method here are right here. And after you've stored in your initial value, what I want you to do is see if you can't follow these commands. Now these commands, if you just type exactly what you have here and then press enter, that should give you this one right here. If you keep pressing enter, you should get what you have here in figure 4. So see if you can't follow this, make sure those things make sense, and try and come up with the root of this polynomial. I'll walk around and help. Right here. Just type in exactly. I've got all the keystrokes you need. Type them in exactly all the way up to It's good. It's really good. Yeah, because I mean, you get to the root pretty quickly.
Oh, right, yeah.
This is your first example of something called an iterative method.
Oh, okay, I got
That's
you.
pretty good. Okay, cool. Yay. Yeah, you did. All right, just keep on pressing enter until these start staying the same. All right, is everyone able to get down to, decimal values that end in 662? Okay. So let's take a look at this. You're going to type in first the x minus vars, right arrow, and then you can type in 1 and 1, or you can type in 1 then enter, doesn't matter, divided by, and then vars again, to the right, y vars. This time you want to choose a second function, and then store that back in x. Now without that store back in x, then your calculator is not going to update the value of x. So when I press enter, I get a new value of x. When I press enter again, it's going to take that value of x and run it in here. So it's going to update it. It's going to continually update it. Enter, enter, enter. And it doesn't take very long before, this thing converges. Take a look at it. There's no change between this one and the next one. So you've got pretty much as much accuracy out of your calculators that you're going to get. So, I'm sorry, I didn't get by over here. Were you guys able to match that? There might be something wrong if you had to click it that much. So work with me on the next one and see if you do it all right. Let's see. Let's check this. There's a couple ways you can check this. One is just to look at the graph. So if I graph this, say, like I have up on the handout, -1 to 1, and -1.25 to 1.25. Then I get a graph that kind of looks like what I have on my handout. You can trace. Here's something cool. Is anyone getting that too? That's your derivative. I don't want that there. Way you can shut that off, if you hit the y = key, and it doesn't affect your calculations at all. Go to that equation, put the cursor on the equals key, and then press enter. If you move away, you'll see that shuts it off. Your equation's still there, but it won't graph. And that's really handy. So if I go back to the graph, now I'm not stuck with that extra equation. You said the cursor, yeah. Put the cursor on it, press enter, and it can switch between off and on. Well, you hit the y = key, and then if I press enter, now I turned it back on. Press enter, turned it off. So returning this, you could hit the trace key, and you could type in, as many digits to that number as you get, as you want until you get bored. But perhaps a better way to check this would be just to plug it in this equation. Let's see here. What would happen if I took my value of x, raised it to the 5th power, added x, and then subtracted 1? What do you think should happen? X to the 5th plus x minus 1. What should I get? 0. That's what I want. Oh, -1. That didn't work too good. Did I type that in wrong? That's not right. What's wrong with that? I must have accidentally stored something somewhere. That should give me a 0. Let me see what I got in for x. Oh, somehow or another I stored an x = 0. Let me go back up to here. Store that in x. There we go. All right. Yeah, with that value of x. Now this time I didn't get quite 0, But do you recognize what that number is? This is a number that's extremely small. What's the e negative 10 represent? Yeah, it's scientific notation. It's 9 zeros, then the 1, 2, 2, 5. So it's a really small number. It's essentially 0. So that's okay. Yeah, it's still probably times something to, the negative 10th exponent or something like that. But let's try a couple more here, and I'll try and work with you to keep up with the calculations. And let's see here. Problem number 18. We're going to kind of get double duty out of this. And I'm going to help you out a little bit. Problem number 18 asks you to find where f of x equals 2 minus x cubed and g of x equals e to the x over 2. Where do these two cross each other? Well, that's not exactly what Newton's method is for, right? Newton's method is trying to find where a function crosses the x-axis, not where two functions equal each other. But we can play with this and make it work in Newton's method. Here's the trick. If we want to find where 2 minus x cubed equals e to the x over 2, that's the same thing as 2 minus x cubed minus e to the x over 2 equals 0. Right? Just move that to the side. So if I let h of x be the difference of these two functions, equal 2 minus x cubed minus e to the x over 2, finding where this equals 0 is the same as finding where those two functions equal each other. So that's the trick. You're going to create a new function, f of x, by subtracting, or h of x by subtracting f of x minus g of x. So let's run through the work in applying Newton's method to this. How am I going to do that? Well, let's start by plugging in the function and then its derivative. So clear out the old stuff. The function is 2 minus x raised to the third power minus e to the x divided by 2. Make sure that 2 is in the exponent. 2 minus x cubed. That's the function that we're cubed. Minus e to the x divided by 2. Now the derivative of this. Well, the derivative of a constant is 0. So I'll get minus 3x squared. The derivative of e. We spent a long time with this earlier in section 3.7. Derivative of e is e to the x over 2 times the derivative of the exponent. What's the derivative of x over 2? What's the derivative of that? Exactly 1/2. So 0.5 times the original function. Do yourself a favor here. Oops, there's a subtraction in there. Second, insert, subtraction. Yes, sir.
Whenever I go to differentiate e to the x, I remember the joke.
Oh, that's cool. Thank you. Good job. Do yourself a favor. Let's shut this off. Shut off the graph of the derivative, and then plot this. Now, the window that I'm going to use is basically, call it -1 to 1 on both axes. It's a little bit bigger on the y-axis, doesn't matter. But graph it. what are we looking for? Looking for where it crosses the x-axis. Now this is going to be your job in some of the problems. So you're going to have to figure out what's a good initial guess. So what is a good initial guess here? Yeah, 0.75, sure. Let's not knock ourselves out. 0.75 looks good. So I'll quit here. Now let's do 0.75 and store it in x. Now you get to reinitiate all this stuff here, right? Yay. But there's a shortcut. Since you've just finished doing this, if you hit the second key and then the enter key, it'll bring up your previous calculation. Well, I don't want that. But hit the second key and then the enter key again, and you can keep on going back to previous calculations. And you should find pretty quickly that calculation. So this is your Newton's method, and you just start pressing enter from here. It shouldn't take long for this to converge to the number you see here on the screen. Are you able to get that number? There's a few of you over here that struggled with the last one. Are you getting it on this one? There's one last thing that I want to discuss with you, and that is Newton's method is a numerical method. There's problems that you can run into when you're working with numerical methods. Things can fail. And I'll show you a quick example in problem 23, and we'll finish with problem 24. Problem 23, we don't even really need to do any calculator work. Let's just take a look at what's going on with problem 23. Y equals 2x cubed minus 6x squared plus 6x minus 1. Let's take a look at what y prime would equal. Y prime would be 6x squared minus 12x plus 6. Looks all right. Newton's method looks like this. X minus f of x over f prime of x. And that's our new guess. They tell us in this one to use x sub 0 equals 1 as your initial guess. Well, let me take a look at that relative to y prime. For y prime, I could factor out a 6. In fact, I can factor this again. Now, as you run Newton's method, you're consistently going to be dividing by the derivative here. That's just a part of Newton's method. Can anyone make a prediction why Newton's method is going to blow up if we started out with x equal 1? The denominator would be 0. Yeah. So right away, as you press enter the first time on your calculator, the calculator is going to come back with error. Now, depending on the problem, there's an easy fix. One easy fix is just to choose a different value for x to start with. If you choose something else, chances are you're not going to land on a place where the denominator is 0. You'll be okay. So, let's see that with problem 24, and we'll call it a day. Y equals x cubed minus 2x minus 2. They give us an initial guess of 0. All right. Let's plug these into our calculator and see what we can come up with. I'm going to plug in the function and its derivative. So x cubed minus 2x minus 2 over 3x squared minus 2. It might be in your best interest to shut off the graph of the derivative and actually graph the function. But, we'll do that later. Once you have those two, let's start with the initial guess that they give us, which is x equals 0. So 0 store in x. Then let's do Newton's method. -1, okay. And 0. And I think this is going to get kind of boring if you keep on doing this, right? Bummer. You're kind of in this vicious cycle. And what's going on is really a function of the graph and a particular value we started with, but we're not getting anywhere, which is kind of annoying. We can change that. We can make that better. Let me move out the x-axis a little bit more. -3. We can probably change that and fix that if we were a little bit closer to the initial value than 0. Is 0 a good guess for where the graph crosses the x-axis? No, it's actually kind of poor. What would be a better guess? I mean, 2 would probably be great. 1.75 would probably be great. Pick your favorite guess. This is what I'm going to have you do on one of the problems for your exam, is come up with your initial guess and run it through. On one of the problems, I'll give you the initial guess, and I'll ask to see the data that you get from the first few iterations and the final one. But let's just pick even 2. 2 store in x, and I'll bet you Newton's method converges pretty quickly. 1, 2, 3, 4. Yeah, 4 iterations. That's all we needed. And we got the right answer. 1.8 probably would have converged remarkably fast, right?
Yeah, then it went back to 1.76.
Yeah, so, yeah. Okay, for homework. One through 7, 15 through 19, 23, 24, which we've already done, by the way, 25, and 27. The last two ask you to find fixed points. So really a fixed point means you're trying to find where f of x equals x. Just create a new function like this and run Newton's method with that new function. See ya!